Welcome. Today is Tuesday, January the 19th, and we are just kind of cruising along through this second semester. We're going to be finished with this chaotic year soon and very soon, I hope. And then pray the vaccines work, that we get back to normal next year and just kind of have a normal life. All right, but we were talking on Friday about entropy, okay? And entropy, Advite, bring it over here, please. Advite is a measure of the disorder of a system, okay? The disorder of a system. Things in nature tend to go to a higher state of disorder. That's the second law of thermodynamics, okay? So, the entropy of the universe is constantly increasing. So the universe is the system and the surroundings. We're going to be measuring the entropy changes of the system. Okay, they can go up and down, but the universe is always increasing. So we're going to be looking at that. Just some common things, and this is just a quick review before I erase all this off the board. Entropy is a more complex molecule, so the more complex the molecule, the bigger the molecule, the more electrons there are, the more vibrations, the more motions there are. So more complex molecules have a higher entropy. And then for ionic compounds, the weaker they're attracted, the lower their lattice energy, then it's going to be the higher the entropy. So again, an NaCl, which is +1 -1 with an MgO +2 -2, the +2 -2 is going to be held much more strongly together, so it's going to have more order, a lower entropy. All right, so those are just some of the common things here. And then on this last thing over on this side is entropy increases when you dissolve a solid or liquid into water. Well, that makes sense because as a solid it's orderly and confined, but then when you put it into water, then all of a sudden it breaks apart. Okay, it looks like I'm missing. Somebody stole some salt out of the middle here. Okay. All right. And so when you put a gas, though, a gas is already random, and you put it into the liquid, the entropy decreases. And then lastly, we can determine the sign of delta S just by looking at chemical reactions. And in the video we went through some, and we'll do a few more in the book on that, is just being able to determine how we determine the sign. It's just if moles of gases are being produced, entropy increases. If moles of gas are decreasing from reactants to products, then entropy decreases. And you just look at moles of gas. You don't worry about solid, liquid, or aqueous. Just compare moles of gas reactants to moles of gas products. And I did several examples of those, I believe, on the video. Okay? And then lastly, this is how we're going to calculate delta S, but it's going to be just like we did delta H. The entropy of the products minus the entropy of the reactants. And this, you get these values, page 1100 on that appendix C, the same one we got the delta H values. The delta S values are there. The only two things that we have to pay attention on that is that the units on entropy are joules per Kelvin mole, whereas delta H are kilojoules, and we're going to learn about delta G today. That's in kilojoules. So when we do anything that combines them together, we got to just make sure the units match up. That you change one, the kilojoules to joules, or the joules to kilojoules. Usually we change joules to kilojoules on this one, and just kind of go from there. Okay. The second thing on this is that elements have an entropy. The only time things have a zero entropy is at absolute zero. And that's the whole definition of absolute zero, where entropy is at its minimum. Okay? So that's the third law of thermodynamics. Yes, sir? Okay, he's in fifth period.
Yeah, do you have your list?
Oh, well, yeah, he sits here by himself.
Yeah. Does anyone sit here?
No.
Okay. He's there by himself.
Yeah. Now, from that chair to that chair, I think we're good, right?
Yeah. Go
guy that I'm talking about got, so we had to check anybody around?
Yeah, for sure.
Okay. Me.
Who's credit?
All right. So, everything, so you know, delta H heats of formation, elements aren't created, so their heats of formation is 0, but every substance has an entropy, and they'll all be listed again on that appendix C. But just don't assume that an element has a 0 entropy like it does delta H. Okay? So those are just the things about entropy. So why are we learning about entropy? Why are we learning about this disorder? Because I'm making you? I mean, what's the purpose? What did I tell you as far as why we're doing this? Okay, let's backtrack. To occur, understand why some reactions occur and some don't. We have two driving forces, two things that cause chemical reactions to occur. What's the first one?
Energy.
What about energy? It favors an exothermic reaction. So what's happening with potential energy in an exothermic reaction? It's being released to the surroundings, so the system is decreasing in potential energy. Exothermic reactions are favored in nature. But that's when I went and did the acid and the baking soda, and it got super cold. Okay? And so when it got super cold, it's an endothermic reaction, but that reaction still occurred spontaneously. It still happened just like that, adding the acid. There must be some other driving force other than energy, because that's an unfavored energy change in terms of nature for it to be endothermic. So what do you see when you pour acid onto baking soda? Gas, a lot of gas being produced. Gases have high entropies. So the fact that we're going from a solid and an aqueous solution and we're producing a bunch of gas, that means entropy is increasing, so it's an entropy-driven reaction. Okay? So the temperature was unfavorable change, but the entropy change was favorable, and the entropy change is more favorable than the energy change is unfavorable, so the reaction occurs. Okay? So we're looking at what causes reactions to occur. So what drives them? What are the reaction tendencies? How do they get, you know, one reacts, another doesn't? And that's why, again, I put my gold wedding band into the acid and nothing happened, because there was nothing driving that reaction. We weren't going to have an exothermic reaction, and it's wasn't going to produce enough gas. So it just sat there. All right. So we have one last concept that kind of puts these two things together, and it's called Gibbs Free Energy. Just as I'm doing this, just to give you a plan for the week. Today is Tuesday. You will not be here tomorrow. I will probably just give you just a handful. I'm going to try not to make it too much tomorrow. Just a couple of problems to work on. Thursday might be more problems to work on. And then Friday, we'll kind of go over all the problems. Probably Monday, Princeton review day, test like on Tuesday or Wednesday. Okay? I like doing the test on Tuesday because I have more of you in class. You're still going to be open book, open note, because the people at home are going to be open book, open note. But at least I get the hard copy, and you know, a lot of people at home don't print out the test. They just put the answers on a sheet, and it's very hard to grade. Whereas when it's on the test, it's a lot easier for me to actually grade. So just plan on a test beginning of next week, Tuesday, Wednesday, for this, because I'm going to finish up. This is only probably going to take me 20 minutes for this last thing, and then we're just ready to put it all together. Okay? Gibbs Free Energy. delta G. Gibbs Free Energy. This is the amount of energy that's kind of left over after we consider the energy change, the exothermic, endothermic, entropy changes, the increase and decrease. It's what's left over. It's the amount of energy that's left over that can do work to actually cause the chemical. Did it stop?
No, it's like, it like was blurry.
Oh, okay. Because I went to the whiteboard and that's what it was. But it's okay now. All right. So, this is the official definition. The amount of energy in a reaction left to do useful work. Okay? And that simply means cause a reaction to occur. Okay? So the work that we're talking about here is making the reaction happen. Now delta G is the gatekeeper for all reactions. It determines really whether the reaction is going to occur or not. Delta G can be calculated, really, we can calculate the delta G of a reaction by a very creative formula. Delta G of formation of products minus the sum of the delta G of formation of reactants. So if we just wanted to straight up calculate delta G, these again are found on Appendix C, page 1100. The table has all three values. This one is do it just like delta H, multiply coefficients times the value. It's real straightforward. But the more useful version of this equation is delta G is equal to delta H minus T delta S. Why is my brain going blank on the sign? Making sure. I've only done this a million times. Delta G, okay, I don't know why I did that. All right, so delta H is your heat of reaction. Delta S is your entropy of reaction. And what's T gonna be? Temperature. And because it's not delta T, what unit must this be? Kelvin, okay? Only when it's delta T can it be either one. Because it's just T, it has to be Kelvin. So, when we're looking at this, delta G equals delta H minus T delta S, this kind of tells us whether the reaction is going to occur. If delta G is negative, the reaction is spontaneous. Which means negative means that there's energy to give. All right, they can release energy to the surroundings. They can do work. But if delta G is positive, the reaction is non-spontaneous. Spontaneous. Now, we're going to use fancy words. Thermodynamically favorable. Okay, so what would this one be? Unfavorable. Okay, so either term, you can either say the reaction occurs because delta G is negative, making it thermodynamically favorable, or it means it's going to be spontaneous. Spontaneous was the words that we used up until probably 5 or 6 years ago, and then APL was starting to come out with thermodynamically favorable. But now I've kind of even seen them go back, use the word spontaneous again. So either one is going to be 100% fine. Okay, so you can just kind of say thermodynamically unfavorable. All right, so delta G, and when we want to know about the spontaneity of a reaction, delta G is the determiner. Or if we go in the reverse, if a problem says our reaction occurs spontaneously, what does that automatically tell me the sign of delta G is? Negative. Okay? So anytime it says a reaction occurs, you know the sign of delta G is negative. Delta G is the gatekeeper for all reactions. It's the ultimate determiner. Okay? Is this a yes? Is this a yes or a no or no? So we have these possibilities. If we have delta G, delta A, well, let's do it the other way. We have delta H, we have delta S, and we have delta G. And I just want to look at the signs. Okay, what's the favorable sign in nature for delta H? Which one does nature tend to want to have? Positive or negative? Negative. It wants to be exothermic. Negative delta H is the exothermic reaction. So that's a negative. What's the favored sign for delta S? Positive. Okay? So if I have my delta G is equal to delta H minus T delta S. If I have a negative here and a positive there, and we know that the Kelvin temperature is always positive, right? So I go a minus a positive. What's the only possible sign for delta G? Negative. Minus a positive is going to be a negative. So that means this is going to be spontaneous at all temperatures. Both of the driving forces are saying yes. This is a good thing. Let's make this happen. Now, it doesn't necessarily mean it's going to happen fast. It may not even happen appreciable at room temperature because it might have that high activation energy where you just got to give it a little bit of a push. But it is going to be a naturally spontaneous reaction. Okay? Paper burning would be an example of a slow reaction. Again, this paper is slowly burning. It's an exothermic reaction when that occurs, and it produces a bunch of gas. So as a result, entropy is increasing, energy is decreasing. It's a thermodynamically spontaneous, but it's not occurring to any measurable amount right now because of the activation energy. It just needs a little push, it needs a match. Okay? So what if we reverse that? We go positive and negative. So now, if I'm looking here at positive and negative, positive minus a minus, what's the only sign? Positive. So what would that tell me? It's non-spontaneous at all temps. Doesn't matter what the temperature is, it's not gonna, there's no way to get a negative delta G. And I don't memorize this table, I'm trying to show you the math, because you guys are all good at math. You can just kind of play around with it with the signs and just kind of see what's going on. So notice that two things are different. These are both saying yes, these are both saying no. Favorable changes, unfavorable changes. But what if we have a mixture? What if it's an exothermic reaction, but the entropy goes down? Negative and a negative. So now I have a negative up here and a negative. So it's minus a minus, so it's a minus and a plus. What's going to determine the sign of delta G? It's whichever term is bigger, right, is going to determine the sign. The only thing that we can change is the temperature. So this one is going to be a temperature dependent reaction. Okay? Now let's talk about, is the temperature going to be high or low? Well, this is really going to be a minus and a plus. right? Because when you do the minus and the minus, it turns it into a plus. So, if the temperature gets bigger and bigger, this term is gonna get bigger and bigger, right? So at some point, this term gets bigger than this term. And so when that term gets bigger than this term, what happens to the sign of delta G? Positive. The reaction becomes non-spontaneous. So this one is only going to be spontaneous at low temperatures. Okay? At high temperatures, this term gets bigger than that term, the reaction stops, and it starts going the other way. Okay? So this can be positive or negative, and it's spontaneous at low temperatures. I don't have a good example of that one. I need to find a good example of that particular case where reaction is only is good at a low temperature. Because most of the time we think you add heat to something that's going to make it react faster. But there are a few that go like this. And by the way, AP on their problems and their they love to ask that one. Okay, you see this all the time. But the other one, the last one, is positive with positive. So if we go positive with positive, now it's going to be positive and negative, right? So what's going to be the case here? Spontaneous at high temperature. It can, again, the sign can be positive or minus. It's going to be spontaneous at high temperatures. Now this is an easy one. This is ice melting. In order to make ice melt, energy goes in. You put ice cube onto your hand. Heat's going to leave your hand and go into breaking the bonds. It's an endothermic reaction. The surroundings of your hand gets cold, right? It takes energy to break the water molecules apart from one another. So it's the energy change is unfavorable. But a liquid has a higher entropy than a solid does. So the entropy is increasing when ice melts. Okay, so the energy change is saying, no, I really don't want to melt. Entropy is saying, no, I really want to melt. It all depends upon the temperature. Delta G has to be negative. So there's a certain temperature at which the reaction becomes spontaneous. What's that temperature? When does ice begin to melt? 0 degrees Celsius or 273 K. And at that point, it's a reversible reaction. When a reaction is at equilibrium, and we're going to learn more about this semester in the next few weeks. When a reaction is at equilibrium, delta G equals 0. So when ice is melting, when it's going through the phase change, remember the temperature remains constant, and it can go back, forwards and backwards at equilibrium. When you're at 0 degrees, it can go forwards and backwards. When the reaction's at equilibrium, delta G is 0. So when ice is melting, delta G equals 0 equals delta H minus T delta S, which means then we can bring that over here and say T delta S is equal to delta H at equilibrium. That's how you calculate the temperature that the reaction's going to change at. It's just delta, that when the reaction's switching over from spontaneous to non-spontaneous, delta G is going to be equal to 0. It's going to be at equilibrium, and you can calculate what T is, and really say T equals delta H over delta S. Okay? And by the way, mathematically, the definition of entropy is the amount of energy change that occurs at a given constant temperature, delta H over T. Now, we're never going to have to solve that or do that, but that's what the technical definition of entropy is, mathematically. All right, so we have two ways of calculating delta G. this form kind of like the Big Mama equation, but this is the one that's probably used much more often. Both are at your disposal. Both are on the equation sheet, okay? Generally, if they just give you delta G information, you're gonna do this, but if they say anything about entropy, you're probably gonna have to use this one. All right? And that's it. So delta G determines everything. Two driving forces. So this is an equation that relates delta H and delta S, but they're really independent of one another. One can go up, one can go down. They don't work in unison all the time. It's just delta G relates the two. I kind of like to think of it as this is your gross pay. This is the taxes. How much energy does it take to change state, to break bonds? How much maybe you're getting a refund, bonds being formed, energy's being released, okay? And so this is your net pay. How much is actually left over for you to spend? Okay, so you got a certain amount of energy being released, certain amount of energy being absorbed. Here you got a certain amount of energy released or absorbed based upon the bonds breaking, bonds forming, as far as do we have more gas, do we have more solid, how's it going? So the energy changes, this is what's left over to actually cause the reaction to occur. Does that make sense? All right, if we go back to, I think it was 2010.
Is T the temperature at which the reaction occurs?
Yeah, and they'll always say that. And a lot of times, what does the degree symbol again mean? I took it off of some of them. If I have a degree symbol on this? Standard temperature, which is 25 degrees Celsius, 298 K. So if they don't tell you the temperature, but it has that, you assume 298. But almost always they tell you the temperature. But again, if they don't and you see the degree symbol, you know the T is 298. 1 atmosphere, but all these are assumed. Anything we do with delta H is assumed to be a constant pressure. That's what enthalpy is defined as, or the heat transfer when the reaction's at constant pressure, which in an open beaker, it's gonna be a constant pressure. All right. Let's see, dig deep down here. Turn this on. Okay, so in the practice problems that I've already given to you, go back and look at 2010 now. I don't know if you have the actual sheet. I think I gave everybody a sheet. Didn't I give a handout? Or just posted them? No. Okay. Okay, so this was the problem. Okay, so we went through and did this problem. Again, remember we calculated the change in temperature, and that's always going to be T final minus T initial. So it was the negative 3.2 degrees. So we make sure we put the negative on there. T final minus T initial. And then because it got colder, what type of reaction is this, endo or exo? Endothermic, okay? And then we went through and calculated delta H for the reaction and then the kilojoules per mole. So you had to do A, B, and C, but then it said to skip D. Are we all, y'all are still kind of digging through your papers there. I can tell. You got your math and your chemistry all mixed in there. You get
Every single class.
yeah. You know they make a thing called dividers, where you can put all the math in one section and all the chemistry in another section. Yeah, I might have some back here that I can share with you. Okay? So, when we look now at D though, and we have to have the answer for delta H. Does anybody have it written right there? We did it together. What was the value for delta H? So in part C, the delta H equal in terms of kilojoules per mole. We calculated this value right here, the molar enthalpy, to be what?
15.2.
Okay,
15.
15.2. Positive or negative?
Positive.
15.2 kilojoules per mole. So is that a favorable or an unfavorable change in nature? Unfavorable, because it's endothermic, it's positive. Okay? So it's unfavorable. Yet the reaction occurs. So what must be driving this reaction? Entropy. Okay? The student, so using the information table, will calculate the value of the entropy of the solution, include units with your answer. So they give you the value of delta G, they give you delta H. So obviously what equation are we going to use? Delta G is equal to delta H minus T delta S. Okay? What are we solving for? Delta S. Okay? So, and notice they say at 298, so they tell us the temperature. So delta G is negative 6.9, so again it came out negative, which is why the reaction occurred, is equal to delta H, which we calculated to be 15.2 kilojoules per mole, minus 298 K times delta S. Let's just plug it into that equation. Oh, accepted value 14. Sorry, I used the 15.2. You use what they give you, 14.0. That's why you guys were looking at it. Okay? So, we subtract 14 here, we're going to get negative 20.9. Is equal to negative 298 K times delta S. So divide by negative 298.
0.07.
Okay? And so delta S is equal to 0. What?
0.07
Just
kilojoules.
and it comes out to 0, exactly that.
701.
701, 3 sig figs. Okay? Now, the units on this are going to be kilojoules per mole. Okay? Because we have 298 kilojoules per mole K, we're dividing, well, did one of the K's not cancel out? Oh no, that's right. Kilojoules per mole K. I was thinking it was on both sides, but I brought it here. So, this is equal to delta S. Now delta S is almost always in joules. Does it even tell us what units? It just says include units to make sure you know whether it's kilojoules or joules. Most of the time you're going to find it being 70.1 joules per Kelvin moles. That's the most common way of expressing that. Now, because it doesn't specifically say, you don't have to do this conversion. You could have left it just like this and been 100% right. Okay? Not too bad. Can y'all see? So when calculating delta H is going to be products minus reactants, then they're going to give you something else. Okay, and just kind of go from there. I'm surprised that somewhere in this problem, because they're telling you the accepted value and then your value, that they didn't ask you to calculate the percent error. Okay, and percent error would have been what minus what?
Yours minus accepted.
Yours 15.2 minus accepted
Over
14.0
accepted.
over the 14 times 100. Okay. That's a common question. And by the way, For those of you that got to do the virtual lab, the one that I did, you know, I videoed it, and I don't know if anybody in here had to do that or not, but my percent error was only 5.4% in that Hess's Law lab when I did it. So just letting you know, the old man still's got it. You know, I can still video and do the lab and get decent results. All right. Seems like there was another one that mentioned delta G in here.
Well, if you got to, you must have done the lab separately. Oh my god, bro, sleepy. Did you not sleep?
Okay. So again, we're in chapter 19. Okay, so if I'm looking at a problem like 50, I am on page 849 in your book, okay? If I'm looking at a problem like this, and it says, gives me this, and it says calculate delta S. All that I have is delta S, so I'm just gonna go, to the back of the book, and I'm gonna do the entropy of formation of products minus the entropy of formation of reactants. I'm just going to look up the values for each one of these things. Again, remembering that elements will have a value, and I'm just going to solve for it. Let's go ahead and just do one of those just for the sake of doing one. I don't think we need to do 20. We can do one. I'm not a math teacher. Math teachers love you to do 20 of the same problem. And then 3 that they never covered in class, that you're expected to know how to do. Yeah, but that one's supposed to be there. There should be another one just like that. All right, we're supposedly trying to do this using page 1100 in the back of the book. Products minus reactants. Let's see what you can do.
Which one?
Let's do 53. Let's do 53D since it has some coefficients. And then you can check your answer in the back of the book. Pay attention to the units. Notice that in the back of the book, joules is in, delta S is in joules. Okay, I know that you're not finished yet, which is a good thing. Without doing any math, how can we predict what the sign of delta S is going to be? Okay, how many moles of gas do I have as a reactant? 5. How many do I have as a product? So what's happening to entropy? More gas, remember, gas is more disordered. So entropy is increasing, so the sign's gonna be positive on this one. Okay? So you should come out with a positive delta S when you do the calculation. So a multiple choice question is something like this, just to determine the sign. Or which one has the greatest entropy increase, greatest entropy decrease, and that's gonna be the biggest difference between reactants and products. Hold on, I gotta start over. Right? 213.6. What did you say it was, Nathan?
188.83.
I'm still right today. Times. Okay, so we're given this equation right here. We can find delta H, delta G, just by using the values back in the back of the book. Notice again that we have to multiply. Moles is gonna cancel on each and every single one of these. So that's gonna leave me with joules per K, which is gonna be what the units are. So delta S of the reaction is gonna equal, what do we get with all that? 92.32. Okay, and it turned out to be positive, right? And that's joules per K. Now, if we wanted to go through and if we had delta H, we needed to figure that out, we would make sure that this joules got changed to kilojoules before we put it into delta G equals delta H minus T delta S. That's where most people make the mistake, they forget to do that. Okay? All right. Go ahead and take your break and come back. It's all